Hi everyone! So before we proceed to our discussion proper, I will first introduce to you some of the terms that you will encounter along the presentation. First one is the single crystal X-ray diffraction technique. So this is an analytical technique which provides the detailed information about the internal lattice of crystalline substances, and this includes the unit cell dimensions, the bond lengths, the bond angles, and the details of site ordering. Next one is the clathrates. So these are crystalline solids which contain guest molecules trapped within the host lattice. We also have the doping. So this is a process where excess electrons or holes can be introduced into the material by the substitution into the crystal lattice of an impurity atom. We also have the charge neutralization. So this is described as highly non-stoichiometric. So when we say non-stoichiometric, this violates the law of definite proportions and its elemental composition can't be represented by a ratio of well-defined natural numbers. So it is also described as the several charges on an adsorbed polyelectrolyte chain which are necessary to neutralize a single charge on the particle surface. Next one is the host molecule. So this is a component in which its binding sites converge in the complex. We also have the guest molecule. So this is any component whose binding sites diverge in the complex. A duct is a product of a direct addition of two or more distinct molecules, resulting in a single reaction product containing all atoms of all components. Next one is the conductive columnar structures. So, like metals, they are characterized by the presence of unfilled highest energy states in the valence band. So, this is a feature that allows the holes or electrons to move down a stack. Lastly is the mesophase. So this is a state of matter intermediate between the liquid and the solid. So one common example of it is the gelatin.
Small molecules in solids play a fundamental role in electronics, photonics, and molecular separations. Small molecules can become assembled in the solid state in several different ways, all of which provide a useful introduction to the behavior of more complex materials. The first importance of small molecule materials is that small molecules often become packed into a highly ordered crystalline three-dimensional lattice. Second is that the formation of crystals from solution or from molten mixtures may yield crystalline solids that contain more than one small molecule species. Third, small molecules in solids may exist in the form of an amorphous glass, in which the molecules are oriented randomly. Lastly, within a discrete temperature range, liquid crystalline state may occur. The first importance of small molecule materials. Small molecules often become packed into a highly ordered crystalline three-dimensional lattice. Such crystalline solids are among the simplest and easiest materials to understand, and they can be studied with great accuracy by single crystal X-ray diffraction techniques. This self-assembly of small molecules into an ordered three-dimensional array may occur not only when the molecules are crystallized from solution or from the melt, but also when they are condensed directly into the solid state from the vapor. The second importance is that the formation of crystals from solution or from molten mixtures may yield crystalline solids that contain more than one small molecule species. These can involve anion, cation, or charge transfer associations, or they may be solids in which neutral guest molecules occupy space between the host molecules. These last systems are formed from molecules that, because of their shape, crystallize with significant empty space in the lattice, into which small guest molecules can fit. They are called clathrates. The third importance, small molecules in solids may exist in the form of an amorphous glass, in which molecules are oriented randomly. This situation is less common for small molecules than it is for polymers or ceramics, but it can occur with small molecules if a molten liquid is cooled rapidly and if the molecules are highly flexible or have irregular shapes. And lastly, within a discrete temperature range, liquid crystalline state may occur. A liquid crystal is a thermodynamic stable phase characterized by anisotropy of properties without the existence of a three-dimensional crystal lattice, generally lying in the temperature range between the solid and isotropic liquid phase, hence the term mesophase.
Now, let us discuss the packing of small molecules in the solid states. The packing arrangement of small molecules in a crystal are determined mainly by three factors: shape fitting, molecular dipoles or charges, and hydrogen bonding. These three factors will be discussed individually in the next slides. First, let us discuss shape fitting. Neutral molecules attempt to assume a minimum energy orientation in terms of the attractions and repulsions between them and their near neighbors. Therefore, van der Waals types of forces are the main influence on the shape-fitting process and the separation between adjacent molecules, while the orientation relative to each adjacent molecule is a result of the energy minimization. More than one packing arrangement will be acceptable and is responsible for crystal structure changes as the solid is heated, cooled, or subjected to pressure. It is also possible to calculate the minimum energy packing arrangement using known or predicted interaction parameters. However, a single crystal X-ray diffraction study is usually quicker to carry out and examine the experimentally determined packing arrangement. Also, as you can see on the figure on the left side, it shows a simple classical example of shape fitting. It shows how a motif in the form of hexamethylbenzene can be assembled on a lattice to generate a two-dimensional array that minimizes the free volume in the crystal. The second factor is dipolar or charged molecules. So, as we can see in the picture on the left side, small molecules with dipoles or separated charges attempt to achieve a minimum energy packing arrangement by bringing the positively charged regions close to the negatively charged parts of neighboring molecules. And as a result of the compromise between charge neutralization and shape fitting, is a crystal structure. So, again, the crystal structure is the result of the compromise between the charge neutralization and shape fitting. So, here in dipolar or charged molecules, X-ray structure is also the fastest way to understand how these factors achieved a balance. We already have discussed the first two factors that affects the packing of small molecules in a solid state, which are number one, shape fitting, second, dipolar or charged molecules. Now, let us proceed to the third and the last one, which is hydrogen bonding. So, although hydrogen bonds are weaker than covalent or coordinate bonds, they still exert a strong influence on packing because of the proximity of the functional groups in the solid state and the limited molecular motions that are possible in a solid. So, crystal structures of molecules such as amino acids, hydroxycarboxylic acids, dicarboxylic acids, phenols, amines, or water are strongly influenced by the opportunities for hydrogen bonding. And a well-known example of a hydrogen bonded solid is, of course, water ice.
An interesting concept in solid state chemistry is the way in which small molecules in solution or in the molten state assemble at the surface of a growing crystal and choose the minimum energy orientation. This process is generally known as crystallization. In crystallization, sample molecules of different orientations are present in a supersaturated solution. The process must take place at the interface, which is a common boundary between two different phases or between adjoint crystal grains of different orientations.
The molecules in solution are forced to crystallize because of their need to conform to the crystal structure on the existing surface. Seeding. Seed crystals are sometimes needed to initiate crystal growth. Seeding is one of the most straightforward methods used to control supersaturation. During seeding, a small mass of crystals is added to supersaturation in order to first, start the crystallization at the desired supersaturation level, and second, provide sufficient surface area to ensure supersaturation is consumed in a controlled way. In essence, crystallization starts with nucleation, and nucleation occurs much faster on nucleation sites, such as seed crystals, scratches, or solid impurities, compared to if they were to crystallize spontaneously in solution. Crystallization can also be formed from agitation since it also increases nucleation. However, rapid growth can lead to incorporation of impurities, which is something you wouldn't want in your final product. Purification by recrystallization. Impurities in molecules are usually excluded from the formed crystal because of the forces that favor the deposition of molecules in an orientation that matches those that already exist at the surface. Recrystallization is the preferred method of purification if the solubility property of two compounds are sufficiently different. So how does recrystallization purify solids? An impure solid compound is mixed with a hot solvent to form a saturated solution. As the solution cools, the solubility of the compound decreases, propagating the growth of pure crystals. If a solution impurity is more soluble than the solute itself, it can be washed off the fully formed crystals with cold solvents. If an impurity is less soluble, it will crystallize first and can then be filtered out of the heated solution prior to the recrystallization of the solute. Application. The purification of silicon for semiconductor use is critically dependent on the recrystallization phenomena. Silicon is abundantly present on the Earth's surface in the form of sand. It is used in a variety of applications, such as the formation of semiconductors. The extraction process of silicon from sand involves heating silica in an arc furnace at about 1800 degrees Celsius. The silicon formed as a result contains a number of impurities, and it is known as metallurgical grade silicon. To extract pure silicon, the metallurgical grade silicon is further ground into a fine powder and mixed with hydrochloric acid. The mixture is further heated until it gets thoroughly vaporized. The crystals of electronic grade silicon then get deposited onto electrically heated polysilicon rods. The electronic grade silicon crystals deposited on the rods have a purity of about 99.9%, and they are gradually pulled out of solution. From the previous lesson, we can remember that the technique of growing crystals from pulling is also known as the Zerchalski method.
Let's discuss about the spherical molecule in solid state. So the simplest mode of molecular packing in the solid state is provided by C60 fullerene, or also known as buckyball molecules. These spherical molecules pack into crystal lattice in a manner described elsewhere for ions or for metal atoms. In other words, because of the spherical shape, the assembly pattern is determined in a most efficient way to assemble spheres in 3 dimensions like a collection of ping pong balls. Now let's talk about fullerene. So Buckminster fullerene was discovered in 1985 and has a perfect sphere with the formula C60. So the fullerenes form a molecules containing a conjugated pi system. Each fullerene represents a closed network of fused hexagons and pentagons. They are carbon clusters whose surface is formed by 12 pentagons and any number of hexagon as shown in the picture. There are two different structures. So figure A shows the crystal packing arrangement of C60 at room temperature. It is a face-centered cubic or FCC arrangement, which means it can be visualized by assembling the first layer of spheres with each one in contact with 6 others. The second layer is constructed from spheres placed in the depression in the first layer. And lastly, the third layer is formed from spheres placed in the depressions in the second layer. Successive layers then repeat this sequence. At ambient temperature, the spheres undergo rotation or tumbling in space within the lattice. However, the presence of metal atoms such as potassium trap in the remaining space in the lattice, as in M3C60, yields a solid that is room temperature electronic conductor but becomes a superconductor when cooled at 18 Kelvin. So the electrical conductivity is a consequence of electrons being transferred from metal atoms to the pi orbitals of the fullerene molecules, and because pairs are in close contact, the electrons are free to move from molecule to a molecule. So here in figure B, the face-centered cubic or FCC structured can accommodate no more than 3 metal per C60 molecule. So, and the presence of the 6 metal atoms, as in M6C60, results in the reorganization of the lattice and the loss of electrical conduction. So, in conclusion, the figure A is the packing of C60 molecules in FCC or the face-centered cubic lattice. Figure B is the incorporation of alkali metal cation into the octahedral spaces in the C60 lattice. So a ratio of 3 cations to each C60 allows the original FCC lattice to be retained and gives electrical conductivity. A higher ratio of cations causes the additional ions to occupy the holes of tetrahedral in the lattice, and the structure is non-conductive.
Hi everyone, I'm Eman and I will be discussing about the disc-shaped molecules and other flat structures. We will learn about their characteristics, liquid crystallinity, and electronic phenomena. In nature, there exists a large number of disc, ribbon, or wafer-shaped organic molecules. To name some, we have benzene derivatives, triphenylene, and phthalocyanines. There are also related species like tetrazine and pentazine, which are ribbon or wafer shaped. A property of many disc or ribbon shaped molecules is their tendency to self-assemble into columns of stacked disc or short ribbons. The molecules in each stack may be oriented perpendicular to the axis of the stack, as if they were plates or saucers, or they may be tilted. The third image shown on the screen is a schematic presentation of the tilted hybrid orientation of the pentynes on photoaligned azobenzene layers and of the star oligomers on rubbed polymer orientation layers. A stack packing arrangement has the potential for two phenomena to manifest. First is a discoid liquid crystalline behavior, or the possibility of electron movement down on a stack. Moving on to the liquid crystallinity from disc or wafer-shaped molecules. By definition, liquid crystallinity is a phenomenon which occurs when a solid is heated but does not undergo a clean transition from solid to liquid at the melting point, meaning that an intermediate phase, a mesophase, is formed rather, and it retains some of the order associated with the solid state. But take note that it has fluidity more like that in the molten state. The importance of a liquid crystalline phase is that it allows molecules to be switched from one orientation to another by means of an electric field. True crystalline solids don't enable this, and the isotropic molten states allow too much random reorientation. Several molecules with a quasi-disc structure, such chloroacetyl benzoate, come together to form liquid crystalline phases. On the other hand, rod-shaped molecules provide the basis of the majority of the research on liquid crystalline systems. Molecules that look like discs or wafers tend to behave like liquid crystalline when they are stuck. This is because of the van der Waals forces that hold molecules together in a stack may be stronger than those that hold molecules together in an adjacent column. So, at a certain temperature, columns may separate from each other, but the columns themselves or parts of the columns remain whole or intact. Even if the columns break up, the molecules may still be aligned in the same direction. And the last phenomenon to tackle is about electronic phenomena from disc-shaped molecules in the solid state. These phenomena are associated with delocalized aromatic molecules. These pi orbitals overlap when molecules are stuck in column in the solid state. This generates a pi system with electron delocalization down the column. In suitable conditions, this yields a semiconductor or conductor-type bond structure, rather than discrete molecular orbitals. But this factor alone does not ensure electronic conductivity. Like metals, conductive columnar structures are characterized by the presence of unfilled highest energy states in the valence band, a feature that allows holes or electrons to move down a stack. This may be facilitated by doping the crystal with species that accept or donate electrons from or to each column. The illustration on the screen is the self-assembly of coronium molecules in the solid state, following vapor deposition. We can see the tilted stack arrangement that allows overlap of the pi orbitals on adjacent molecules.
In this section, we will be focusing on rod-shaped molecules or calamitic liquid crystals. Most liquid crystals are thermotropic, which means their orientation and periodicity depends on temperature. They are typically rod-shaped with a long and rigid center that allows them to maintain their shape. They also have flexible ends, so they flow past each other with ease. They tend to align themselves pointing along one direction or linear director vector. A director vector gives an indication of orientational order in liquid crystals. There are two kinds of subphases for liquid crystals. One is the nematic phase and the other one is the smectic phase. In the nematic phase, nematic means thread-like. The rod-like molecules are aligned in the same direction but are free to move around much like a liquid. They have orientational order but have no positional order. Their order can be controlled or realigned by an electric field, so this is applied for making sharp images in liquid crystal displays. In the smectic phase, which means soap-like, the rod-like molecules are arranged in separate layers that can slip over each other, hence the soap-like nature. They have orientational order and have some positional order within the layers. There is another class of nematic liquid crystal called chiral nematic or cholesteric crystals. It has a helical structure, therefore its director vector is rotated slightly in each layer of molecules. The distance along the axis between two molecules with parallel vectors is called the pitch. It is actually made from mixing nematic and chiral substrates or esters of cholesterol. Cholesteric LCD screens are better than common nematic LCD screens because they can be viewed even with bright sunlight.
Charge transfer complexes, molecular assemblies of two or more molecules or ions, referred to as charge transfer complexes or electron donor acceptor complexes. Two molecules self-attract to each other by electrostatic forces to form the assembly. One is at least partially negatively charged, while the other one is partially positively charged. These two are referred to as the electron acceptor and donor. In some instances, the degree of charge transfer is complete, allowing the CT complex to be categorized as a salt. Oftentimes, the charge transfer association is weak, and polar solvents can quickly break up the interaction. Formation of electrically conductive crystals by co-crystallization of tetrathiophulvalin and tetracyanokinodimethane. The two planar molecules that form stacks when assembled in the solid states, the stack structure allows overlap of the pi orbitals in neighboring molecules within each stack. This provides a pathway for electrical conduction. The pure tetrathiophulvalin is not an electrical conductor, but it can relinquish an electron to form a radical cation, and the partly oxidized stacks are semiconducting. The conduction behavior can be visualized in terms of the electron moving in one direction through the tetracyanokinodimethane stacks and positively charged or holes moving in the opposite direction along the tetratiofulvalene stacks. Tetracyanokinodimethane become electrically conductive when doped with metals or the solid circles. The semiconduction does not require the presence of both tetratiofulvalene and tetracyanokinodimethane in the same solid. The other electron donor or acceptors will serve the same purpose. For example, is the salt. The tetratiofulvalene and the chlorine is a semiconductor, with the semiconductivity resulting from the movement of holes along the tetratiofulvalene stacks. The tetracyanokinodimethane also forms conductive charge transfer complexes with coronium, in which the two components alternate down the tilted stacks.
Let's proceed to clathration. So this phenomenon often occurs with the host molecules that have an unusual shape and prevents them from packing efficiently to minimize energy. So the guest molecules occupy the free volume in the lattice and help to stabilize the solid state structure. In some circumstances, two or more different host crystal structures exist. First one is the guest molecules, in which the host molecules attempt to make the best use of the available volume. And second is that the arrangement when the guest molecules are present. So because this phenomenon depends on the solid state structure, dissolving the crystals in a solvent or volatilization of the host breaks up the adduct. A wide variety of small molecules form crystalline clathrates, and a few examples are shown in this slide. They range from organic molecules such as hydroquinone and urea, and also the cyclodextrines through inorganic organic molecules such as cyclophosphazenes to totally inorganic species such as water.